Okay, so my new friend on YouTube, Ask Joe, we're both from Staten Island. I think he still lives there. Anyway, so he did a video called Using 32-Bit Float with Extreme Gain Settings on Mix Pre 2. Does it eliminate setting gain? Now, his answer is yes, both qualifications. My answer is no, again, with qualifications. And I feel like we're sort of talking past each other in the comments. So this video is for you, Joe, I guess. So I'm going to answer your argument is essentially always that, well, okay, but I've tested it and it works. Like the audio sounds better to me when I'm have my gain up really high and I'm using the 32-bit float, recording. And I'm not going to dispute that. I'm not going to dispute anybody that says I've used the equipment and it works well to me and this setting is better than that setting. Again, not going to dispute any of that. All I can do is explain how I see this stuff working, explain it sort of in a scientific sense, and you can draw what conclusions you want from it, okay? And it doesn't make a difference what we say scientifically, right? If we like the result, we like the result. But I'm just going to explain some of the scientific issues here and what I think you don't quite get about 32-bit float. So we're going to start. And we're going to start by imagining a single electron. Actually, let's go back further. Let's imagine a single air molecule. So my voice right now, I'm speaking, which means that the air molecules are, there's energy on the air molecule and it hits the next one, and it keeps hitting them. And then it will hit the diaphragm in this microphone and it will push the diaphragm ever so slightly. And although this is a condenser, I'm going to talk about dynamic type. And the diaphragm is going to push past the magnet and it's going to be converted into a push of an electron. So the pushed air molecules, but we're going to talk about one air molecule, it's going to lead to the push of one electron. So one electron is now going through the wire, right, to my audio interface, the one electron. So the question is, do we want to measure that electron or do we not want to measure that electron? So if we really want to measure that, we don't know whether that electron is noise, if it's coming from my computer fan over here, or it's just random electrical noise like a photon from the sun came through the wire. We don't know where that electron came from, whether we want to record it or not, whether it means anything or not to us. And we have to keep that in focus. That one electron we need to measure. Now, when we set the gain very low, we're generally saying, well, we've listened to electrons like that, and we don't want that electron because it's noise. If we set the gain high, we're basically saying, well, we have listened and we want that electron because that electron is part of the audio that we want to capture. Now, the way a preamp works is it takes that electron and it basically goes onto a scale, in a sense. There's another feed of electrons. So you have the one electron, and let's just say you have a million electrons. You have a million electrons in this tube, essentially. And what a preamp does is it says, okay, I want to set, when this electron hits this tube, let a million electrons pass. We're going to match a million electrons to the one electron. If we have two electrons, we're going to make 2 million, right? So you're going to get this one-to-one relationship between the electrons coming from the microphone, which are very few, to these large numbers of electrons, these large voltages coming through a separate line, which is what we want to use in place of the original electron, because we're going to measure that. We're going to use that to save the strength of these electrons into our computer memory. And I have to go into that over and over and over again. The electricity from a microphone cannot go through a modern day electric circuit and write to memory. It is not strong enough. And it's not that we take these electrons and we add a bunch of them. We say, oh, hey, you're one electron alone. Let's add it. We'll give you a bunch more. We see you. We see you're one, and we'll give you a million. It doesn't work like that. It works physically. And I'm going to explain that you see this in the real world everywhere if you choose to look. So I have two scales here. I have a scale to measure packages that I'm going to send through UPS or whatever, the mail. And I have a scale here that measures my body weight. So this scale will measure in ounces, and this scale will measure in pounds. Okay? So the question is, why don't we just have one scale for everything, right? Why don't we just have one scale? Why do we need two scales? Why on electric voltmeters do we have for millivolts, volts, megavolts, whatever? Why do we have different gauges in our electrical equipment? Because we have to match the scale of our amplification or the scale of our measurement to the strength of whatever it is that we're measuring. And we can't, there's no physics, there's no physical device that can do it for everything. It's sort of like a scale like this, right? You can put, 10 grams on the scale, and if you measure anything between, let's just say 2 grams and 20 grams, it's going to work well. But if you put a kilogram on here, right, it's going to just wreck the scale. And it's the same thing the other way. If you put a kilogram weight on the scale, and then you bring something that weighs a few grams, will it move the scale? No. And it's the same thing in electronics. It's the physics of it that's everywhere in every sort of device that we work with. So when you set the preamp, you're essentially setting what kind of scale you're going to use. Are you going to use, a scale that's very sensitive to low electrons? You can use a scale that's very sensitive to high electrons, and you're going to have to balance out what you want. Now, if somebody puts something too heavy on the small scale, let's just say that you have high gain, low gain. It's put something too high when you have low gain. The scale will max out. You won't get a reading. Similarly, if you put something too low on the scale when it has very high gain, you're gonna get a lot of noise. I don't know if I had that correctly, but you get the idea. So anyway, so we're thinking about this one electron that's matching the one molecule. You can't predict what electrons you're going to want ahead of time. When you set the gain, you're predicting what kind of balance you want, how you want that stream of electrons that you're going to use to mirror that first stream, how you want to set that up to accurately mimic it. And again, you can't have it both ways. And I think the thing, Joe, that you keep missing is that once you measure that one electron, it's like the Heisenberg principle, part of it. Like Heisenberg says, you can figure out the vector, you can figure the position of electron, but you can't figure out both at the same time. Similarly, just like Heraclitus says, you can't step in the same river twice. Once you step in that river, once you take that stream of electrons from your microphone and you set the proper weights to it in its amplification, you can't go back and remeasure it. So when I hear multiple ADCs, I'm like, ADCs to what? Right. So an analog to digital converter is saying, okay, I can take an analog signal and digitize it, right? But you can put an analog digital converter on any kind of voltage, right? But it doesn't mean that you can redo it again. So how can you have 4 measuring the same stream twice? It's sort of like saying, okay, I can put my foot in the stream and I'm going to measure it, and I'm going to put another. You put your foot, Joe, in the stream. I'm going to put my foot in the stream after it, and we're going to measure it, and we'll be able to detect, how strong that stream is. Well, we can't, because your foot already altered that stream. It already interacted with that water in a sense, right? And it's the same thing with microphone. Once those electrons hit the preamp, they are gone. One time and one time only. So, okay, you get the electrons that hit the preamp, create the stream, and then you put another ADC on that stream. But what are you accomplishing, right? You've already optimized your amplification of the original signal. If you let's say set the gain too low and you didn't measure those electrons, how are you going to get them back in that amplified signal? They're gone. You lost them in the first and only amplification that you can do of the original signal. So that's like the main thing. Like theoretically, you would have to explain to me, and again, I'm not saying don't use 32-bit float or whatever they're doing. You'd have to explain to me how you can have multiple quantizations of an original electronic stream, because I just don't see how it's possible. Okay. And again, it's not that I'm saying, oh, theory says you can't do this or that. It's that if you accept this theory, you sort of understand, well, what can they do? What are ways to deal with it? So the ways that they've dealt with it in the past, they came up with this in the 1930s, when the original radios came out, is they said, okay, we have our amplified, audio, let's just say, right? And we look at it and it's really high. Not the original microphone electrons, voltages, but what's coming out. So, well, this is really high. So go back to the preamp and lower the gain a bit, right? Because it's too high. Or same thing, if it's really low, then increase the gain. But it's after the fact. But if we're doing spoken word, we're not going to really notice this stuff if it happens in milliseconds. But that's how limiters work. They're a lot electronic way of basically they don't look at the that they're measuring, they're amplifying the original microphone thing, but they're using an amplification saying if too hot, go lower it, too low. But it doesn't change. Like when it goes back, when a limiter or an auto gain goes back and changes the gain, in a sense, the weights of how it's counting these electrons, it can't change what it already measured. That's gone. So when you record that, that's gone. So the reason people don't use limiters they might not use limiters in audio is because of that very problem. When you get to your recorded track, yes, and somebody starts talking really loud and the limiter kicks in, it pulls it back, right? But when they start talking softly again, let's say, there's a little part of time where the limiter hasn't reacted yet and that audio is subpar fidelity because you just can't go back in time. You can't predict how strong electrons are going to be or sounds are going to be or anything like that. But again, you can put in mechanisms that will adjust as it looks at the strength of these things. And that mechanism will work in the sense that it will prevent clipping or whatever in certain circumstances, but it's at a cost of fidelity. Now I want to talk about 32-bit float for a second. So 32-bit float, you show these things, it's much more numbers. You can put a lot of numbers in it. Yes, but I really wish you would go read about how 32-bit float works. It's called float for a reason, and it has a cost. And again, it has a trade-off that are well known. I'm not making this stuff up. This isn't my own theory. You can go read the history of computer data. So the way that 32-bit float happened is that if you're using, let's say, 24-bit, right, and you have 16 million values or whatever it is, I don't remember. But let's just say you have like 16 million values. Okay, so you're doing your spreadsheet, and you say, I want to talk about the budget of the state or the country, and I want to talk about billions or trillions. Well, how are you going to store a billion or a trillion in a data space where your maximum number is 16 million, right? Well, you can't. You would have to actually make two cells and say, okay, well, you know what I'll do? Maybe what I'll do is I'll use these two cells, these two 16 million number. I'm not going to tell you like what you could do, but I'm going to tell you how it works. So the way it works is that 32-bit float or floating point data basically says, okay, what we're going to do is we're going to take these 16 million values, which are completely precise, and we're going to use exponents to make them larger. So if you want to talk about a billion, let's just say, we might say it's 16 million to the third, right? So 16 million times 16 million times 16 million. And this is done in binary, which adds another complexity. But anyway, essentially the way that 32-bit float works is it takes these very precise numbers and it uses exponents to raise them to these large numbers. But the drawback is that these large numbers are not precise. You can't store, let's just say, 1,543,333,000, blah, 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 0.777. You can't. You lose some precision. But it's accepted that, if you're working on finance, you're working with these large numbers, you don't need this high level of precision. So you throw it out. But in audio, we want precision. We don't ever want to throw out precision because it's all relative. Each level of sound has to be equidistant from the other because the electron, it's linear. It has to be all equally spaced. And in 32-bit float, Yes, you can space it out larger, but you're losing precision within everything. The only precision you can guarantee are the 24 bits of the mantissa. The mantissa is the number, the core number that you use before you raise it to an exponent. When you raise it to an exponent, you are getting an imprecise number. And in fact, you can do different calculations to get the same number. You can use like mantissa A with exponent B to get the same number that you could use like mantissa C with exponent D. Okay, you can look all this stuff up. So 32-bit float is inherently imprecise. Though again, it's no real different than 24-bit in audio, because as long as you keep all your values are in that mantissa space, equally spaced, then you're going to get the same thing you would get in 24-bit. You throw out the exponents, which are imprecise. And the other problem with 32-bit float is because, as I said, it requires two numbers, or three if you want to talk about negatives and positives. But let's put the signage away. You need two numbers. You need a mantissa, right? You need one number, and then you need the power that you raise it to. When we get back to that single electron, we want to measure that single electron. What is that single electron in exponential math? Like, how would you even like measure it in that way? What electronic device would the electron hit and then say, oh, well, this is the mantissa and this is the exponent? None. You would have to record it as a value, as a single value, a single count of electrons, and then say, okay, what's a 32-bit float representation of that number? And again, that number will be, or can be, imprecise. It's mathematics. There isn't no mathematician is going to argue about that. I mean, you could not win that argument against anyone. You can go to, ChatGPT, anyone, and ask it. You could say, in 32-bit float, is how many precise numbers can 32-bit float represent in bits? It will tell you 24 bits. You can go ask this question. You can go read the articles. And so you're making me like have to call you, say things I don't want to say, right? You have to do the research. I'm sorry, you're just plain wrong here. So 32-bit float, because it is imprecise, and because microphone voltages work in a linear fashion and tap out, according to all audio engineers that I've read, at 12 bits, some say, okay, I'll even say 16 bits. In other words, no electrical engineer that I have read has ever said that a microphone can resolve past 16 bits of linear data information. So getting back to the spreadsheet, that's sort of like saying if our maximum number is 16 million, but the numbers we use are only going to ever reach 10 million, why do we need a billion, right? We don't. We don't, because the original data never fills doesn't even fill the space we've given it. So when Sony first came out with their digital recorders, they made them 16-bit. Why? Because they did all this science. And they worked with all the microphones and analog equipment they had. This is just the beginning of the digital revolution. And they said, we can't resolve past 16 bits based on the electronics, the physical materials. Because again, these are all materials inside, silicon and doping and whatever they put in this stuff. They're actual physical things you can touch and feel, though of course they're very small. So they did that and they said, this is it. We can get 16-bit. And then it came out 24-bit because it's easier to master stuff and do effects and whatever. But again, there's no need to record anything in 32-bit float to have that range, because nothing produces that range. You can write into that range, sure. So I don't know what Sound Devices is using to take that original audio and write it into a 32-bit range. I just know that I don't see, understanding the evidence that I'm giving to you before, how it would make a difference. So where am I? So I'm at almost 20 minutes. So number one, you can only preamp a signal once. You cannot get back information from the original microphone stream of electrons once you preamp it. Now you can do computer modeling and analyze and say, oh, look, it looked like there's going to be a peak here, and I'm going to, yes, you can take the sound of clipping or the actual clipping data, and you can make it sound not clipped. As you point out in some of your comments, yes, there's software that'll analyze it and do it, but you cannot get back that original source. Once you preamp, once, it's one and done. Secondly, after you do that, you end up with a data set from 1 to whatever that is below 16 bits in resolution. After that, you're just talking about noise. You're just adding more and more noise to your signal. You're not getting anything past it. So to go to 32-bit float, to go to 32-bit fixed would give you nothing, because actually going to 24-bit fixed actually gives you nothing with the microphone. And you're using the word float, you're letting your imagination run wild about what this float means. It doesn't mean what you think it means. Yes, as you point out, it's increased dynamic range, but it's not increased dynamic range with the same fidelity or precision as 24-bit. It only matches 24-bit and 24 bits of data, because that's what's its mantissa. Once you use the exponents, all bets about precision are off. So anyway, here's my quick video. I hope you are well. This is a lot of fun. And on to the next comment or your next follow-up video. And I'll try and do a better video that explains all this with diagrams and blah, 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 that.